Hi everyone, I am Madam Rosmaya. In this video, we are going to discuss on impedance of a series RCL circuit. We have discussed before in the previous lessons, resistance, inductance and capacitance have very different phase relationships to each other when connected to a sinusoidal alternating supply. For alternate current through a resistor, I and V are in phase, and for alternate current through an inductor, V leads I by pi per 2 radians, and for AC current through a capacitor, I leads V by pi per 2 radians. The fundamental passive linear circuit elements are the resistor, capacitor and inductor. So these circuit elements can be combined to form an electrical circuit in three distinct ways. So what is impedance? Impedance Z is measured of the total position, is the measure of the total opposition to current flow in an alternating current circuit. It is made up of the sum of two components, resistance and reactance. In other words, how much the circuit impedes the flow of charge. So impedance is measured in ohms, same as resistance. However, the total impedance is not simply the algebraic sum of the resistance, inductive reactance and capacitive reactance, since the inductive reactance and capacitive reactance are 90 degrees out of phase with the resistance, and therefore their maximum values occur at different times. Vector addition must be used to calculate impedance. Okay, we discuss here in the first circuit RC in series. For R, I and V are in phase, and for C, capacitance, I leads V by pi per 2 radians. So if we draw the phase diagram, the amount of voltage across the resistor is represented by the length of the horizontal line, VR. And the amount of voltage across the capacitor is represented by the length of the vertical line. So their angles between the two VR and VC is pi per 2, 90 degrees. Therefore, using vector, the amount of resultant voltage Vz is represented by the length of the diagonal line. And the angle between Vz and VR is called phase angle. VR is equals to IR and VC is equals to IXC. XC is reactance, capacitive reactance. Because current I is constant, so the phase diagram can also be drawn using R and reactance. So if the amount of resistance R is represented by the length of the horizontal line, and the amount of capacitive reactance XC is represented by the vertical line, then the amount of the impedance Z is represented by the diagonal line here. Since the line form a right angle triangle, so the Pythagoras theorem can be used to find the length value of the impedance line. So this is the Pythagoras theorem. So for this application, the variable A is equals to the resistance, B is equals to the capacitive reactance, and C is equals to the impedance. So the equation becomes Z impedance equals to square root of R squared plus XC squared. And for phase angle, psi, tangent psi equals to VC per VR, because we use trigo ratio where tangent psi equals to opposite per adjacent. For the second phase diagram, we can use XC per R. Okay, if we substitute XC equals to omega C, the equation becomes like this. And if we substitute omega equals to 2 pi f, so the equation becomes like this. Z equals to square root of R squared plus bracket 1 per 2 pi FC squared. Okay, next we see variation of impedance with frequency. We are going to plot the graph impedance against frequency. So R is constant, so we draw a straight line here in the graph. So if F increases, okay, refer to this term, if F increases, the terms 1 per 2 pi Fc will approach 0. So therefore, Z equals to square root of R squared, and at Z is equals to R. So this means Z approaches R for high frequency. So how to draw the graph? So the graph is a curve, downward curve. In other words, Z approaches R for high frequency. So far, if we plot the graph I against F in the same graph, from V equals to Iz, V per I equals to Z. So the Z here decreases. So F increases, Z decreases, so therefore I increases. So the graph refer to the red line curve here. So F increases, Z decreases, and I increases. And then at F0, I is 0 as the capacitor blocks direct current. Okay, we've done for the RC circuit in series where we get impedance Z equals to square root of R squared plus XC squared. And the graph is the graph Z against F is a decreasing curve. Okay, for RL circuit in series, for R, I and V are in phase, and for L inductor, V leads I by pi per 2 radian. So if we draw the phase diagram, the amount of voltage across resistor is represented by the horizontal line here, and the amount of voltage across the inductor is represented by the vertical line here. And their phase difference is pi per 2 radian, which is equals to the 90 degrees. Therefore, using vector, the resultant voltage Vz is represented by the diagonal line. And the phase angle between Vz and Vr is psi. And from formula, Vr equals to IR, VL is equals to IXL. XL is the reactance for inductor. And current is constant because the circuit is in series. Therefore, the phase diagram can also be drawn using R and XL. So using Pythagoras theorem, the equations impedance Z equals to square root of R squared plus XL squared. And the phase angle using tangent psi equals to VL per VR. And for the second phase diagram, we can use XL per R. And we can substitute XL equals to omega L into the equation, and also we can substitute omega equals to 2 pi F into the equation. Okay, from this equation, Z equals to square root of R squared plus bracket 2 pi FL squared, we can see the variation of impedance with frequency. So by plotting the graph or sketching the graph, impedance Z against frequency. So R is constant, we draw a straight line here. So F increases. If F increases, refer to the equation here. If F increases, Z also increases. So therefore, the graph is a curve, upward curve or increasing curve. And then at F0, Z is equals to R. So if we substitute F0 here, we get Z equals to square root of R squared, and that means Z equals to R. So this is the conclusion for the RL circuit in series, where Z impedance is equals to the square root of R squared plus XL squared. and the graph Z against F is a increasing curve. Okay, next for RCL circuit in series. For R, I and V are in phase, and for C, I leads V by pi per 2 radian, and for L, V leads I by pi per 2 radian. So we draw all in one phase diagram. This is VR. I and V are in phase, so we assume direction is to the right. And the VL, voltage across inductor, represented by the upward vertical line, because V leads I by pi per 2 radian, and the angle is 90 degrees. And then the amount of voltage across capacitor is represented by the downward vertical line, because I leads V by pi per 2 radian. So that's why we draw it downward. Okay, refer to this VL and VC only. VL is upward positive and VC is downward negative, so we get VL minus VC. So the resultant for VL and VC only. And lastly, the resultant for these two lines with these two voltage. So we get Vz. So the Vz, the resultant voltage, is represented by the length of this diagonal line. And the angle between Vz and VR is a phase angle. So from Vz equals to Iz, so we can use Pythagoras theorem. So Vz equals to square root of VR squared plus bracket VL minus VC squared. Okay, substitute Vz equals to Iz into the equation. VR equals to IR, VL is IXL, and VC is IXC. And the I here can be cancelled out. So therefore, the impedance Z is equals to square root of R squared plus bracket XL minus XC squared. So this is the equation for impedance for RCL circuit in series. And we can substitute XL equals to omega L and XC equals to 1 per omega C. So we have this equation. And if we substitute omega equals to 2 pi F into the equation to see the relationship between Z and F, the variation of impedance with frequency. And from the graph impedance against the frequency, refer to this equation. R is constant, so combination of RCL, we get this graph. And at the minimum point here, the frequency is called resonant frequency. The resonance of a series RCL circuit occurs when the inductive and capacitive reactances are equal in magnitude, but cancel each other because they are 180 degrees apart in phase. So at resonance, the impedance of the circuit is purely resistive. So why it is purely resistive? We can refer to the equation, this equation, when the inductive capacitive reactants are equal in magnitude. So that means these terms XL minus XC is equals to 0. So leaving the equation becomes Z equals to square root of R squared and Z equals to R. So the sharp minimum in impedance which occurs is useful in tuning applications. Example, the application of resonance circuits is the selection of FM radio stations by the radio receiver. Next, we are going to derive the equation for resonant frequency. From this sentence, the inductive and capacitive reactants are equal in magnitude, so we can write as XL equals to XC. So substitute XL equals to omega L and XC equals to 1 per omega C and equate them. And then omega is equals to 2 pi F, and the F used here is resonant frequency, because we are going to determine the resonant frequency. So we substitute F naught. They are equals at the resonant frequency. We can cross multiply. F naught times F naught is F naught squared, and 2 pi times 2 pi is 4 pi squared. So therefore F naught equals to square root of 1 per 4 pi squared LC, and square root of 1 is 1, square root of 4 pi squared is 2 pi. So the resonant frequency equation is F naught equals to 1 per 2 pi square root of LC. So combine all in one graph, we get the impedance of RCL circuits drawn here, where F naught is equals to 1 per 2 pi square root of LC. And in the previous lesson, for reactance, shown by the green line here, decreasing, or in other words, reactance X is inversely proportional to the frequency, and for the XL, reactance is directly proportional to the frequency, all in one graph. Okay, so this is the conclusion for RC circuit in series. Z equals to square root of R squared plus XC squared, and the graph is a downward curve, decreasing curve for impedance against F. For RL circuit in series, Z impedance is equals to the square root of R squared plus XL squared, and the graph is the increasing curve for graph Z against F. And lastly, the impedance for RCL circuit in series is square root of R squared plus bracket XL minus XC squared. And the graph is shown here. So that's all for this video. Thank you for listening and watching.